There were folks who were going to measure the radiation left over from the Big Bang, the cosmic microwave background, and they were going to very precisely determine the state of the universe as it existed shortly after the Big Bang. And we have a new model of the universe, which goes by the sexy name Lambda CDM. How do I go from the early universe to the late universe? We invoke dark energy shortly after the Big Bang in a period called inflation.
Is there a way to reconcile this without having to invoke another tooth fairy?
Yes.
You invoke Santa Claus.
Exactly.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. And I got with me co-hosting.
What's up?
How you doing, man?
I'm good, buddy. Good
Paul
to see you
Mecurio.
again. Good to see you again.
Professional comedian. You got your own podcast.
Yeah, Inside Out.
Out and In.
There you go.
In-N-Out Burgers.
Yes.
Did they sponsor you?
Yes. For those listening and watching, this is how not to host a show. Have a guest and not know anything about it. Yes, it's called In-N-Out Burger, and the whole podcast is me interviewing people in the drive-through window.
In the drive-through window.
You want fries with that? So, you're an astrophysicist. The guy was on my podcast.
I was.
Along with Paul McCartney, by the way.
Oh, no, okay. All right.
What do you mean, okay? That's all you say?
Name dropper.
Yes.
But none of that impresses me as much. You've got like a Peabody Award and an Emmy Award. This is for writing. You've been
writer on the Daily Show, and I worked on the Colbert Report.
We love you, man.
I love you too, man.
Thanks for spending some time with us here.
Absolutely. Always great.
Making this happen. You know what we're going to talk about? Mm-hmm. The cutting edge of cosmology. Because everybody's talking about cosmology all the time. Mm-hmm. But who gets in there and say, where's the edge?
Yeah.
And where are people at fisticuffs?
Yeah. we like to mix it up here. Where can we get people at each other's throats?
At each other's throats. Because then that's actually, the history of science shows that's how discoveries emerge.
No, I have to say, I've been doing a few of these with you, and this one is really cool, really interesting, because there is a lot of back and forth on this, and it's really compelling.
Yeah, no, it's good. And a lot of people, contenders, I think, is the way to think about that.
Yeah.
So we combed the universe to find who would be ideal in this conversation. And we found an old friend and colleague of mine, Adam Riess. Adam, welcome to StarTalk.
Thank you for having me.
Welcome to my office here at the Hayden Planetarium.
Excellent.
Yeah.
I was just wandering around the museum and you guys pulled me in. So.
He was with a bunch of children. He was and his hand was being held by a teacher. He might be brilliant and have a Nobel Prize, but apparently he gets lost in large spaces, everybody.
So you're at the Johns Hopkins University.
Yeah.
You're the Bloomberg Distinguished Professor there.
I am.
Bloomberg, he's a friend of my wife who worked for him. He has a background in physics and engineering and came through Johns Hopkins.
Yes, he did.
And donated a whole building called the Bloomberg Center for Physics and Astronomy. Yeah, so there's some good Bloomberg action down there in Baltimore.
And then he ruined everything when he created bike lanes in New York City. I'm telling you, let's spend an hour on that, Mr. Nobel laureate. Can we fix that?
Says the man who does not ride a bicycle.
Exactly.
Okay. Many people don't know that the Space Telescope Science Institute which was responsible for receiving all the data from Hubble and other telescopes, spaceborne, is co-located on the campus of Johns Hopkins University.
That's right.
So you also have a position there as well.
That's right. That's where we have the joystick.
Okay.
I'm going to leave that right there.
We have to add that you are a Nobel laureate.
That's right.
That's badass.
Yeah.
And I think if you had a business card, just say Nobel. That's all. You don't need anything else.
No phone number.
No phone number.
You just think you want to talk to him. He's so smart, he calls you.
So remind me, what year you won that?
We won it in 2011.
You won the Nobel Prize, and that year was split three ways. So who were the other two recipients?
Brian Schmidt and Saul Perlmutter.
And Saul, I remember, was a West Coast guy.
Right.
He
led the Supernova Cosmology Project.
Okay. With the same intent of making the kind of measurements you were making.
That's right.
With Brian Schmidt.
Right.
Okay.
Right. And we were members of the High Z Supernova team.
High Z would be high redshift.
Correct.
Supernova team. And it was given to you specifically for discovering
the discovery of the accelerating expansion of the universe.
Which today we just call dark energy.
Well, dark energy is, we think, the driving mechanism for the acceleration. But there's still a lot we're trying to understand about the nature of dark energy.
Well, get back to work.
Please.
So, I'm going to say welcome to StarTalk.
Thank you.
Yeah.
It's an honor to be here.
Yeah. And so you are co-discoverer of because growing up, I don't mean growing up as a kid, I mean coming through school, in graduate school, we always knew that there was this term in Einstein's equation that it referred to like a negative gravity or something. It was mathematically legitimate, but no one had a negative. What is that?
Nobody accounted for it.
No, what is it? It's just a math thing. So every time we had a conversation about the expanding universe, you had to explicitly say, we're going to assume this is zero. Because what are we going to do?
It's expanding at a constant rate, basically.
Or expanding only according to what the galaxies tell it to do.
Got it.
This would be an extra thing going on, okay?
And you were just too lazy to explore that?
No.
Is that what happened?
No, apparently this gentleman was not too lazy to explore it. And he's saying, I wonder if that is a thing, okay? And there you go. Wait, so first, catch us up on being co-discoverer of the accelerating universe. There are these equations that I'm describing here, and you're getting data. What was your data?
Sure. So, so as you said, this term that Einstein had put in, which he actually put in for a good reason. At the time, he thought the universe was static, and so this term was needed to balance the attractive gravity.
Otherwise, the universe would just collapse on itself.
Correct. Then it would just collapse. And then, so astronomers at the time told them the universe was static because they thought the universe was the Milky Way galaxy. They thought that was already everything. And of course, it turns out there are galaxies out there. They're moving further apart. Hubble and others showed that. And
Hubble the man.
Yes.
Hubble was a man before he was a telescope.
Yes, that's right. It's more like the RoboCop version of Hubble.
But he would be mistaken for a telescope at a lot of parties.
That's right.
He had the shape of a body of a telescope.
The famous story is that once Hubble showed that Einstein that the universe was expanding, in which case it was unnecessary to have this kind of repulsive gravity to balance things, and it was kind of dropped to the side. But as we know in physics, once something is possible, it is always there unless you have evidence that it doesn't exist. So,
right. Very important bit of scientific wisdom there.
So let's jump to the 1990s, and astronomers are looking for...
that was the 1920s.
That was the 1920s, yes. So we're in the 1990s now, and astronomers think there's some matter in the universe, and the question is there enough matter to stop the expansion of the universe? Like, launching a rocket, does it have escape velocity from the gravity?
Is that matter something that would later be called dark energy? Is that sort of...
No, this is what we call dark matter, at the time. We knew there was a lot of matter. Most of it was dark. We knew this because there was extra gravity, the rate at which galaxies or stars orbited galaxies, the stars would have flung out if there wasn't this extra matter. So we knew all that. And then the question was, is there the critical amount, the amount that would halt the expansion, or would the universe expand forever? And so by the late 1990s, the best way to do this was to measure the expansion rate of the universe in the past and compare it to the expansion rate in the present and see if it was slowing down enough to stop.
And this is where the distance ladder comes in terms of measurement.
Yeah, how do you know how far away? I mean, nearby, it's hard enough just nearby. I guess you can use parallax on stars.
Right.
But these stars are sitting on our noses.
That's right.
And we have whole galaxies nearby and beyond.
Right.
So what method, you had to really refine a method to do this.
Yeah, so parallax is great. Having a tape measure and running it out somewhere is great, but these just don't work very far.
You can get those at Home Depot.
Yeah, I know, but not one that long.
With your Home Depot tape measure, you can get to things that are walking distance of you.
Right.
All right. But there are stars out there that, you can't do, radar beaming to them because they're light years away.
So you have to use parallax, a form of geometry that had its limitations because of the angles of the geometry.
You're just trying to make up for getting something wrong a minute ago.
I didn't.
It's pretty good.
But that's good. You did good there.
Yeah.
You did good.
Yeah.
So if you have your two eyes, and if you can put your thumb, and you just look at your thumb with one eye, and then you switch eyes, and then your thumb is moving back and forth.
Hang on, I need a manicure. Jesus. Wait, what am I doing now?
Yeah. You look at with one eye and switch eyes, and your thumb will shift back and forth as you shift.
Right.
It turns out the amount that shifts and the distance between your two eyes uniquely determines how far away your thumb is.
Which is then used.
So try this. Put your thumb here and do the same thing. So now it separates even more.
Yes.
So that's an angle. You can measure the angle. We know how far your eyes are. You know exactly how
Let me
far
do
away
this
your
with my
thumb
hands
is.
so I don't have to look at you. Well, that works. Either way.
I'm blotted both ways. So, what are our eyes? How do we do this with astronomically? Well, you can take a picture of a star, and there's a background stars behind it, and then 6 months later, take another picture of that same star. Now, the width of your eyeballs is the diameter of Earth's orbit. Now, that's good.
So now you can measure.
Now you get that, and you see how much it varies. You know how the diameter of our orbit, bada bing, we get the distance to it. And we have sent telescopes into space to measure this exquisitely, far beyond what's even possible from Earth's surface.
Right. Hubble and then Webb.
Very reliable. No, it's a telescope called Gaia. Gaia, Gaia.
Yeah.
So now we trust these because it's like geometry, we got this.
Right.
But now you have to go beyond that, and you don't get to use parallax.
Right. So then you have to use another method, okay? And there are methods that we use here on Earth, like a lighthouse. So if you're a ship captain, you want to make sure you're far from shore. You want to make sure a lighthouse, which you know is very luminous, looks very faint and assures you, wow, I have to be far away. And we can actually do that quantitatively by measuring how bright the lighthouse actually appears. So
I like that analogy. It's a good one.
In the past, there was a class of pulsating stars called Cepheid variables that have this wonderful property that they tell us whether they're a very luminous lighthouse or a not very luminous lighthouse, depending on how frequently they pulsate. And they're about 100,000 times the luminosity of the sun. And so the big advantage is if you want to measure far, you better have a very powerful lighthouse.
Right.
And so they were good for a while, but we had to go out much further.
That's the second rung of the distance ladder, right?
Yeah, I think
Sure,
so. Yeah,
it
we'll call
is.
it that.
We could say that.
It's the third
We could
one
say-
after the Home Depot tape
Okay, right.
measure.
Yes, that's right.
So you said something important there. 100,000 times brighter than the sun, which means the sun at those distances, we would just never even see it.
Right. That's right.
It's not
That's
useful.
Right, that's right.
Yeah.
So the name of the game at this point is to be able to measure truly cosmological distances very far out. We're really just in search of an ever more luminous standard candle, something that you can just see far away. If you can't see it, you can't measure the distance.
And
to
for
it.
me, explain the standard candle, and that my understanding is that we don't really know what that luminosity is.
So a standard candle is any object whose luminosity is uniform. So when we see a standard candle and it's uniform, when it appears dim, that tells us it's far away.
Right. And we know that we know why they're uniform. That's been determined.
Correct. We know we start out with very good theoretical understanding, and then ultimately we have empirical understanding, which shows us that. So by the 1990s, these Cepheid variables are just not luminous enough. We really need things that are billions of times more luminous than the sun, because we now want to look so far back that the universe has changed, that the universe is younger, that it was expanding at a different rate. So this requires us to go back billions of light years.
So it's like when you're a kid, you shoot up one summer. Neil's like
In height.
Yes.
Or shoot up drugs. I don't know. It's you.
I don't know what you were doing. In
I
those
don't know what
summers.
I don't know what kind of
Most of
child.
us were just
I'm
trying
from
to
the streets, everybody. I grew up on the streets. No, you shoot up in height. Like in
Okay,
one
yeah.
summer,
Fine.
you go from 4'9"
Okay.
to 5'9".
Okay.
But then as you get older, it progresses slowly. So that's sort of the idea here. In very rudimentary terms, when you're going back in the early stages of the universe, you're looking
You're going
at
back to the younger. Yes. Right.
where the expansion is faster.
No, we don't know that yet.
Right.
Well, it could be.
It could be slower.
Right. So let's not jump the gun. So by the late 1990s, we had known about supernovae. Gosh, going back to the ancient Chinese, a star would suddenly appear where you had saw nothing, and we came to realize that these are exploding stars that are billions of times the luminosity of the sun.
In fact, the very word supernova, nova means new in Latin. And so a really bright new thing called supernova, and only we would later learn that the star dying at the end of its life.
Right.
Yeah.
My wife calls me a supernova.
Dying at the
I don't know
end
how to
of
feel
your
about that. But anyway,
He's still in therapy. We'll let him.
I didn't mean to look in your eyes when I said that.
so what we came to really realize in the 1990s is there's two completely different ways nature produces this kind of supernova explosion, and that's very important. One way is you have a very massive star that loses its ability to produce energy at its core. And producing energy was the way it produced pressure that held back gravity. And so it's a very dangerous thing for a star like this to lose the ability to do that. It's basically lost its structure, and so it will implode, followed by an explosion. And those are very bright. They're great, but the problem is they come over a wide range. That could have been a very massive star, or a medium star, or that could have been a star that when it collapsed turned into a black hole, in which case we'll see almost nothing.
So they're not as reliable as a standard candle.
So it's not going to be a good standard
not
candle.
Not a standard candle.
But it's not a good standard candle.
Yeah.
And then we realize hiding in this distribution of all kinds of different exploding things was a subclass that were all the same. And that is a completely different mechanism. It's called a type 1a supernova. And that occurs when you have the core of an old star, like our sun will become, called a white dwarf, which is in a very special state. It's holding itself up against gravity because of quantum mechanics, really. And it can only be stable up to a certain mass, known as the Chandrasekhar limit, after the famous Indian astrophysicist Chandrasekhar, who in the 1930s showed that a star could only sustain itself up to about 1.4 times the mass of the sun. So now imagine this. You have a white dwarf star. It's sitting there. It's less massive than this Chandrasekhar limit. Maybe it's in the mass of our sun.
And minding its own business at this point.
It's doing nothing, and it would be happy that way. It would just cool off and live its whole life that way, cooling, radiating. But what if it has a friend? And, with friends like these, who needs enemies? These are a star orbiting that star, and they get too close, we think, and mass starts to transfer over, we think, and the details of exactly how this occurs are debated. But somehow
how the mass transfers is not clear.
Exactly. Whether it's like they actually merged or it was a gradual process.
Can I just say something between Einstein and you guys? You seem to leave a lot of stuff off to the side. And we're not sure, but we'll just go whatever.
Well, because he's after the consequence of what happened.
That's correct. That'll be clear in a minute, okay?
Yeah.
Okay.
So anyway, somehow mass transfers over, and when it reaches that Chandrasekhar limit, it's like, boom, a thermonuclear explosion runs through the star, okay? And what's so great about this is they always blow up at just about that same mass, very close to that. So this is a standard candle. This is something you recognize it far away. And how do we recognize it? It has a certain spectrum. It has a certain chemical fingerprint.
And this was observable within the Milky Way because that was a distance that we could observe this, or we
could observe these beyond. We could observe these at some of the most distant galaxies.
Because of the telescopes,
right. Now, they're incredibly rare. There's only one in a galaxy like ours per century, but there's no real limit of galaxies. So if we can take a wide enough image that contains hundreds of thousands of galaxies and then come back, a month later, what turned out to be, so unlikely to happen is like guaranteed to happen. It's like winning the lottery because you buy all the lottery tickets, right?
Chuck, last year we all went to your comedy show.
Yes.
Right here in Manhattan.
That's right.
And what was the title? What'd you call it?
It's called Chuck Nice, Just Smart Enough, because I sit next to you.
No, we love you because you have a science literacy and you don't let anything by.
Yeah, well, I took that and I put it in a comedy special, and you were there in the audience.
Do
And
you have a clip you can show us?
absolutely. And just like if I were on The Tonight Show, I have no idea what it is. But check it out. I am too lazy not to believe in God, okay? Because when you ponder the origins of the universe, that gets very, very deep. A singularity, just that by itself. Something that is infinitely hot and infinitely dense. How can it be infinitely dense? At some point, you can't pack shit in anymore. Like what? And at that point, I'm just like, God did it. December 30th, you'll be able to come to StarTalk and you'll be able to see the whole comedy special. So bring in the new year with some science, dumbass. Please head to the StarTalk watch page on YouTube and tap Notify Me so you'll get a ping when we go live. And then we'll watch it together.
Be there. And you began this in graduate school, if I
Correct.
remember correctly.
Yes.
And that whole group.
With
who's the head guy on that group?
Brian Schmidt. And Bob Kirshner.
Bob Kirshner, right.
And the Chilean group for the Kalantololo, which you know very well.
Right. Mm-hmm.
And so what changed the game was in the 1990s, we both came to realize this class was special. It wasn't like the other supernovae. And the advent of large cameras by those standards on telescopes that had a big enough field of view that you could simultaneously stare at 100,000 galaxies and actually have a chance to do this experiment, actually find supernovae on demand.
Right. So you didn't have to wait around for one to show up and then look at it.
Right.
You would like, we're going to find 3 supernova tonight.
Right. And it was actually quite amazing because back in the day, when the Hubble Space Telescope was a new thing and it was incredibly valuable to get time, we would propose for time and say, we'll tell you exactly where the supernova is on Tuesday, so you can start observing it Thursday. And they were like, "You're gonna what? Like you're gonna tell us where a supernova is on Tuesday?" And we're like, "Maybe Monday night if the computer's operating fast
And
enough."
they're like, I got a dinner. Can we hold that off?
But it was, if we had bad weather or something, it was scary too, because it was like, and if we don't just stare at blank sky, which is no astronomer wants to use the most capable facility to just like stare at nothing.
Right.
This type 1a supernovae are visible halfway across the universe.
That's right.
But they're only useful as a standard candle once you can calibrate those that are closer, that have some overlap maybe with the Cepheids. Is that right?
For the discovery of the 1990s, that the expansion of the universe, and here's the big spoiler alert, that it was accelerating, not decelerating. You don't even have to calibrate them because you're only using them as relative measures. You're saying how much was the universe expanding back then relative to how much it's expanding now, even if I don't know
So
an
that
absolute
basically
number.
divides out. It's not
divides
even
out.
It's
there.
like
Yes.
Neil is handsome, but relative to me, not so much.
Okay.
I'd forgotten that's an important.
And it's a very important. So
very
the
important
two
fact.
stories we're going to tell disconnect in that way.
Yeah.
And so by the late 1990s, even if I didn't know the true luminosity, was it 10 billion solar luminosities or 8 billion solar luminosities? What I could say is, that distant one was so faint that it is, 10 times further away than this one, whatever the true
But you've got
luminosity
you've got a
was.
history or an
He's got it.
experience of sort of
So you got a whole string of pearls
Right.
through
That's right.
time
That's right.
and space.
It's
So
almost
that was
like you're a
super
super
clean.
sleuth in a way.
Yes.
It's like you're a detective sort of
Yeah.
using evidence.
Yes.
But
Yeah.
within the distance ladder, you have these 3 rungs. And what strikes me
Four
is...
rungs.
4 rungs, sorry. You have...
Right.
Only
But
have
this is,
to
to be
measure.
clear, this entire discovery of the accelerating universe only depended on one rung internally to itself. So
Yes.
that
But if
we
a
didn't need-
Cepheid is a sort of got a... so if dust affects its brightness,
Yes,
right?
that's important.
So now... That rung is sort of there's some weakness in that rung which can propagate through the rest of the distance ladder. So how are we accounting for? There's so much we don't know. Dust,
Yes.
right, or other components that
Yes.
could sort of affect
Yes.
one rung of the ladder. Could then sort of throw off the
Yeah.
entire calculation.
Or even dust in
that's
your
right.
even in your relative comparisons, the dust would give you the wrong distance.
Right. So when I was a graduate student, this was the part of my thesis, was to figure out how to contend with dust in these type 1 supernova observations. So it turns out that dust makes things dimmer, which would fool you into thinking it's further away. That's very bad.
Right.
Okay, but it does something else too. It makes light look redder when the light passes through it. So look at a sunset, right? Not only does the sun look dimmer, but it also looks redder.
So if you're
the-
seeing the red, then you know there must be dust.
Exactly.
But
And
but
you
then
could
how do you
quantify that.
determine how much dust?
You look at some supernovae where there is no dust, like it's way far out of its galaxy, or it's the bluest one you've ever seen, or something like that.
So the
That helps
power
you
of the
calibrate
red.
against
Correct.
the dust metal.
The redder it is, the more dust.
Right.
Yeah.
And in fact, if you really do this right differentially, all you need to know is it's so much redder than other ones, and then that affects
This
how
is
much
amazing.
difference it is.
Oh, yeah.
in
It's like
distance.
that you're sort of you're getting these pieces of evidence and
Yes.
building. That's fascinating to
Right.
me.
So much science happens that way. People think it's just one question and one answer and one experiment.
Yeah, it's
no.
techniques,
Oh,
lots of
oh my
techniques.
gosh.
So much.
Well, what's striking me in all of what you do, not so much Neil, but you, is you hit a roadblock and find a way around it.
Right. Yeah,
And that's-
no, it's
that's
all solving
most of your-
problems.
That's we need
That's
clever
most-
people.
That's
yeah,
exactly.
On the team.
It's fascinating.
Okay, so now, if I remember correctly, the goal wasn't so much to measure this Einstein
No.
term, was it?
No idea. No, in fact, wasn't even on my radar
It was
screen.
just to lay it
No.
out. It's just to see what's
It was-
going on.
It was just to measure how much the expansion was slowing.
Okay.
Right? And was it
So
slowing
tell me
enough
about your
to-
equations.
Yeah.
Tell me what you
So I'm-
wrote stuff.
I
you-
wrote
you-
stuff
you-
down. Yes.
Okay.
So I wrote down some standard equations of what should have worked for the data, which
Right.
is
Equations anyone would know. Just I want you to know.
And you thought you were thinking it was slowing down the expansion.
And not only that, I was so
this.
sure it was slowing down because that's what everybody told me, and I was in graduate school at the time, was that I said, okay, so the supernovae will measure the slowing, and I'll immediately convert that to what is the mass density of our universe, this famous number called omega m.
And then apply that to our universe and extrapolate.
Right away, yes, but right away that number tells you what we want to know. If omega m is greater than 1, there's so much matter in the universe, it will recollapse. If it's less than 1, it will expand forever. Omega m equal 1 is called a critical universe, or the critical, it's the mass it's the gravity and mass that the Earth would have to have to launch a rocket and have it be escape velocity.
So is this the big freeze, the big rip, and the big crunch?
No, we'll get to that.
Okay.
We'll get to that.
Right. So can you catch up? Because I'm
working on it.
So anyway, slow for you.
So I had come on, guys. I got stuff to do. There's a supernova happening in an hour.
Yeah, that's a good point. You've been listening. So there's a very simple sequence here. Is supernova measure deceleration related to how much matter is in the universe that's causing the slowing expansion. Mm-hmm. So when I wrote my computer program, I said, hey, computer, fit that and tell me the answer. And the answer it spit back was negative mass. Okay. Whoa. Now, there's no such thing as negative mass. That's not like a physics option. But, computers don't know physics. And so you give them very simple instructions, measure deceleration, turn into mass, and I hadn't yet noticed that the data was saying the universe was accelerating. So it was like, okay, you want me to make that equation work? I'll just flip the sign over here on matter. Now it's negative. And I'm like, that isn't right. You can't do that in physics. We can't report that. And so after doing a lot of checks, I was like, well, what could do that? And then, it was like all the classes we ever took was like, Einstein once had suggested something that could go the other way. You put that into the equations and it fit like a glove.
Bada bing.
Yeah.
And you've got, it's not just expanding, but it's accelerating in its expansion.
Correct.
And now it's Y, and that gets you to dark energy.
Right. And so what is it? So,
you made the measurement that it exists.
Right.
Which is a separate thing
absolutely
from knowing what it is you
from the
measured.
Interpretation. Yeah. And,
right.
And just to mention,
people need to needs to sink in here because
the universe is accelerating. Whatever's doing it.
Yeah, we can make measurements of things even if we don't know what's causing it.
Well, it's how some of the greatest things happen. So you're going for A, and then you find B, and this is going to sound as a writer in a room in comedy shows. You could give us an assignment, write a joke about, I don't know, airplanes travel, right? And nothing great comes. And then just out of that comes a great side bit that ends up being, that's how the Back in Black segment came about at the Daily Show. Because
with Louis Black.
Yeah, because we were trying to come up with great jokes on these little stories like a Florida man. And we're like, we don't know what to do with this. Or like, give it to him and let him rant. So it's the same, it's obviously in the arts, but it's the same thing. You're going for one thing, and in a beautiful way, it's like a beautiful mistake in a way, or whatever.
But it's also the thing that still to this day we don't know for sure or understand well. I mean, we could say the universe is accelerating. There's no question about that. But what is causing it? We're still relying on Einstein's cosmological constant, or more generally, dark energy. But we don't understand the physics of that at all.
Well, get back to work, dude.
Yeah. Well, I'm an
what are you
observer,
doing here?
You made the discovery. Now I expect part 2 of this.
Oh yeah. Well, actually, there's something stuck in my pocket.
What?
I've been sitting on it, and it's like bothering me. You ever get like a pebble?
Yeah.
And you're like sitting, and it's like, oh yeah, this.
Oh!
Wow!
Wait a minute.
There you go.
Wait a minute.
Wow! Did you buy that on the street?
Wait. Yeah,
actually, it's in the gift shop downstairs.
I got a guy.
Don't bite it because it's
who's
chocolate.
Got bling that's bigger than this. At the club.
Hanging out with
just for context, right? They didn't give us the Nobel Prize for discovering dark energy, but for discovering that the expansion is accelerating.
Yeah.
Right.
That's why if it would be bigger if it was more significant.
Like
it's just a little discovery, so they give you the baby. This is the baby Nobel Prize.
That's right.
I'm sorry.
So I guess that's Alfred Nobel on the cover.
It is.
On the cover there.
Yes.
Very cool.
Yeah.
Is this actually gold?
Yeah.
Or is it gold? Like,
Let me touch it.
It's I don't know what it's 18 karat or something.
18 karat.
I know it's worth
He
a
gave
lot
it to me.
today.
He gave it to me.
It's worth a lot today. Have you seen the price of gold?
Yeah, 4,000.
I'm worried walking out on the street with this. There's a funny story about
Like the
Brian
game
Schmidt
show.
taking his on the airplane, and the TSA agents were very confused because when they X-rayed his backpack, it just showed up as a hole in his backpack because the gold
doesn't
just
go through.
absorbed all
right.
the X-rays,
Yeah,
and they're
it doesn't
like,
go through
"What
it
is
at
in
all."
your backpack?" And he was like, he took it out, and they go, "What is that?" And he said, it's a Nobel Prize. They said, "Who gave that to you?" He said, "The King of Sweden." What did he give it to you for? For discovering the accelerating expansion of the universe. They were deadpan, though. So
Basically, this guy discovered that you wouldn't be here if I wouldn't be talking to you right now. Can I just say something? You're brilliant, and I'm impressed with that. But I'm more impressed that you're walking around New York City with that in your pocket.
I hear people are nice here.
So then it doesn't come with a thing around your neck,
No.
like the swimmer, you know.
Yes, like
yes.
it's Mark Spitz. We had 7 of them. or whatever.
Stay modern here.
No, I'm going with Mark Spitz.
Michael Phelps.
I was a
Michael
swimmer.
Phelps.
Michael Phelps.
Michael Phelps.
Yeah.
This is heavy.
Yeah, so it's probably
This
got at
is
least
no-
a little.
this is
we got to give it to Archimedes
Nobel.
and figure out how much gold is actually in it.
And Neil, where did the gold come from that was in it?
Oh,
wait.
supernovae!
Oh,
my God!
It's all
Come
coming
on.
full circle.
Oh, full
circle.
circle.
Wow.
They said, in fact, they said, we want to give you something that really represents the work you did. And they was like, let's find a supernova by Tuesday and we'll get some
There you go.
little bits and we'll make something.
Listen, I know a guy that can melt that down into a watch if you want. That's beautiful.
You surely know here at the American Museum of Natural History in our backyard. It's our yard, but it's run by the city. The city controls it, including the dog run. But there's a monument there put there by one of the Swedish
Right.
pharmaceutical companies.
In the Teddy Roosevelt Park.
In the park, and
Yes.
it's in honor of all the American Nobel Prize winners. And my boy's name is on that statue.
They're all carved.
They're
there.
chiseled in.
Yeah.
My boy's on that statue. Right there near the dog run.
Are you saying dogs watch it as they poop?
Did it pee?
So what? We live on 79th Street, right around the corner from here.
yeah.
My dog pees on your name. all the
Really?
time. I'm sorry.
No,
I didn't
my
mean
name
to-
is actually pretty high up. You would have to.
I have
you'd
a very big
seriously
dog.
climb up.
My dog is well endowed. That's all I'm saying. He can reach high.
Okay, so say what you said again because it's important. You got this not for knowing what dark energy is,
Right.
but for the discovery that it exists.
For the discovery that this phenomenon, the universe accelerating, exists, which everybody attributes to dark energy because normal gravity from matter doesn't do that.
Doesn't do that.
It goes the other direction. It's
It
like
goes the other
having,
direction. Hence
it's like
your
driving
negative sign that showed
right,
up in
it's
your...
like having a car and like all you've ever done is hit the brake and then one day the car just takes off and you're like, how did the brake do that? And it's
Yeah,
like, no, a
yeah.
different pedal, the gas pedal did that.
And I think you've started to move toward the idea that dark energy determines the fate of our universe, right?
It
And
does.
that's where it becomes, which makes you a real Debbie Downer. But there's big freeze, there's
Yes.
big rip, and there's big crunch.
Yeah.
Which actually feels like
don't
Ben and
think
Jerry's anxiety flavors. Like,
Yeah.
you would be the big freeze because you're closed off emotionally. You would be the big rip, you're strong, and I'd be the big crunch because I'm a baby. And everything collapses.
The big crunch, I think, is not in the cards.
Actually, everything's on the table still, to be honest with
Really?
you. And in light of some more recent results on dark energy where it may look like it's thawing or weakening.
Well, let's get into that.
So we will.
Let's
We
get
can.
into that
Yeah,
right now. We're all up to speed now.
Yes.
And we have like 3 minutes left.
Yeah. So the universe is accelerating.
Okay.
And we have a new model of the universe, which goes by the sexy name Lambda CDM.
Okay.
Which encompasses everything we know about the universe. The lambda part means there's dark energy.
This is the astrophysicist version of a standard model.
Correct.
I guess.
Correct.
Okay.
Right. And the CDM part is cold dark matter. It means there's a lot of dark matter in the universe. But there are other things in that description, like the universe is relatively flat. There's a certain number of neutrinos, particles. It's everything we know. It's an inventory of the universe, but 96% of it is still kind of unknown stuff. In fact, very unknown
96%,
stuff.
that's the dark matter and dark energy combined.
So by the early 2000s, it was recognized, well, we want to understand this more. And so there were folks who were going to measure the radiation left over from the Big Bang, the cosmic microwave background, with a series of satellites, WMAP, Planck, and they were going to very precisely determine the state of the universe as it existed shortly after the Big Bang. The folks who were measuring the cosmic microwave background got a very beautiful baby picture of the universe that has a lot of fine-grained information about the state of the universe. And
Excess radiation, for lack of a better term.
but it's a description of what the early soup of the universe looked like. What were baryons, normal matter, how much was dark matter, photons.
A really important snapshot of what was going on. Yeah.
And so the great success was the picture they got of the universe was the same model that we were essentially seeing from these more local observations. There's a lot of dark energy, there's a lot of dark matter, everything fit. Except one thing didn't fit, which is it also predicts how fast the universe should be expanding today. And that number, called the Hubble constant, is something we also can learn by this route that we've been describing, where you measure parallax and you measure stars and you measure supernovae. And using that route, you can measure how fast the universe actually is expanding today. It would be like, having a 2-year-old kid. You measure their height, right? And then you predict how tall they'll become. And then you measure them when they get to that full height. And what if it was off by like a foot or something?
Right.
You'd say,
you'd disown the kid.
Yeah,
you're disappointed.
You're right.
He's still in family therapy.
Yes, I understand. The fact that these two routes from the early or late side of the universe, on the one hand, tell us the same rough, more than rough story.
Basic story.
Yeah, like they're like doppelganger universes, except one is younger and expanding faster, and one is older and expanding more slowly.
That's the 71 and the 67.
The 73 and 67.
You want to explain
Right.
that to
The
folks?
numerical
The
values,
numerical values.
That's
of
right.
the Hubble constant.
That's right. And this Hubble tension emerged about 10 years ago.
Tension as in the two numbers are not agreeing.
As in the two numbers are not agreeing.
Now, I have to butt in. I'm in graduate school, and we're fighting over whether the Hubble constant is 50 or 100.
Yeah.
And so you're telling me you're now fighting over whether it's 67 and 72, whatever. And I don't have sympathy for that.
No, but Neil.
My whole time in graduate school, we didn't know the size of the universe by a factor of 2, and you're up to complaining about a few percent.
So now,
Get out of here.
And leave your Nobel Prize.
Let me
Melt
let
that
me
down
tell
and go to
you
dinner.
why this is so much more interesting than that was.
Oh, okay, please.
When people were measuring 50 or 100, they were measuring the same thing. They were measuring how fast the universe is expanding here today, often measuring the distance to the same galaxies, the same stars.
different
When you say
techniques.
here,
you
today, you mean within the Milky Way?
Right,
Well,
or just outside the Milky Way.
Our region, our
So-
part
so
of the
what-
universe.
Okay.
So what so if I told you the length of this table is such and
Good
such,
point.
and Neil said no, I get a different answer. The table has one length, right? And so this is something. It's not that profound. One of us is making a mistake. The big difference here
Very
is
important point.
we are measuring opposite ends of the universe, and we are using our story of the universe to connect them. And so disagreeing in this case has the potential to teach us something profound about the universe, whereas disagreeing back then just meant people were making mistakes.
And when you say profound about the universe, our understanding of physics and the possibility that there could be new physics out there.
Right. Because how do I go from the early universe to the late universe? I need a function. I need a piece of math to tell me how do I translate from there to there. It's like that kid, they were 2 years old, then they're an adult. How did you guess how tall they would be? Well, you had a growth chart, right?
Yeah.
The growth chart is our model of the universe.
It's a formula.
But, with a growth chart for a kid.
But it's not precise.
Well, you've seen a lot of kids grow up, right? So you have a lot of confidence in the growth chart because they follow that. We only have one universe, and most of it's made of stuff we don't really understand.
Right.
Well, get another universe then.
Well, so
Work
if
a
we
little
got
harder.
some- right.
Yeah.
So the fact that they disagree, and Neil makes a good point. It's not a big disagreement in absolute sense. It's like 9%, but our measurements have gotten so precise that it's 5 or 6 times the error bar between them.
I've banned the term error bar because no one knows what the hell that means.
Okay.
The uncertainty.
Sure.
The measurement of the uncertainty of each of those two quantities does not leave room for overlap.
That's right.
Okay.
So
there you go.
from someone who's not as bright as, well, him, I'm saying. Now, could it be that this means that dark energy is shifting? Like,
Yes.
sort of like a petulant
it could be-
teenager, like it's calm and steady,
Well,
and then all of a sudden, you never understood me, Einstein, and it's slamming the door on you, right? Like, is it that possibility? Is that happening?
Yes. I would say that we may be discovering that what we call dark energy is a general phenomenon that happens all the time in the history of the universe. So let me tell you this. We invoke dark energy shortly after the Big Bang in a period called inflation to inflate the universe, okay? We give it the name inflation, but it's dark energy, okay? We have the universe currently accelerating now. That's dark energy.
By the way, it was called inflation because the idea was advanced in the 1970s when we had like 18% inflation. So the word had a lot of currency.
I
didn't know that. Is that right?
Yes, it was under President Carter, and inflation was like 20% inflation.
The win button, whip inflation now. Remember that win button?
We have something in physics that's an important part of physics called the Higgs field, which is a field in space that gives rise to mass for particles. That is an energy, an invisible energy in space. So this is a regular feature now in physics, is to recognize that there are invisible energy fields. And in Einstein's theory of gravity, an invisible energy field plus Einstein's theory of gravity automatically has this consequence of giving a push to the universe.
Ooh.
And so I would say at this point, we are sort of watching the universe to sort of try to learn when episodes like this may occur. Maybe there's only 2, maybe there's 10.
Is that the new, that there's, from my understanding, there's 5 possible reasons for this Hubble tension. Is that the new dark energy theory? Or is that the early
so there's
dark
an early dark energy theory which
Right.
posits a 3rd episode of dark energy. Not inflation, that was the beginning, not the current one. So
Is
it
that
would
the
be
turbo
in between.
boost one, or is it something different?
I don't know about the turbo boost, but it goes by the name early dark energy. But it's the same concept, is that, if you give a kick somewhere along the way, then using the simple form of the cosmological model to connect 2 endpoints, you're not going to quite get things right.
Doesn't it have to be motivated to manifest itself? And so what would manifest a pulse of dark energy in a place unexpected?
Right. It usually ties to a particle, and it usually ties to some event, some symmetry breaking or something like that. And it becomes very theoretical. I mean, theorists argue that sounds reasonable. That doesn't sound reasonable. To me, they all sound kind of like la, 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 la. But, I look at it like, all right, how many times have you invoked the tooth fairy in this conversation? And, I've learned that like a close cousin of the tooth fairy is not a new invocation of the tooth fairy. It's just her cousin. And so to me, there's a big tooth fairy that we've already been living with for a long time.
Sure.
And these are like revisits of the tooth fairy.
All right, so
I'm an observer, so this is not, I look at stuff.
is there a way to reconcile this without having to invoke another tooth fairy?
Yes.
You invoke Santa Claus.
Exactly.
Well, first of all,
Big fan.
there are a lot of
He
ideas.
needs better gifts.
Yeah. One way to play the game is to change the way the universe looked before this radiation from the Big Bang leaks out. So
How do you change the way it looks?
So change our understanding of it.
our understanding
We're
of
not
it.
changing
Right,
it. What do you
right.
think we
That's right.
God?
Right.
What-
So
what do you-
it's a kind of a
Tooth fairy,
plasma
maybe.
soup. And
Yeah.
so even something as subtle as saying if there was a magnetic field in it that could start this process of collapsing by
Or there
gravity.
could be new particles. Isn't
There
that
could be a
another-
new particle.
there's-
That is
that's
absolutely another
theory,
possibility.
right?
It rearranges the way energy is distributed in the early universe. And so there are many ideas: electron mass decaying, interactions between dark matter. See, when physicists start out with the cosmic microwave background, they have to build a model of what's going on in the universe. So this would be like some new attribute going on there, or it could be something late in the universe. Like as dark energy emerges, it's not this cosmological constant, which means static, uniform, unchanging, but it has some kind of mind of its own.
Right, so you have your option to either make the early universe match the current universe, or the
Or
current
the-
universe
exactly.
match the other,
That's
or have
exactly
them
right.
do something both
Right.
that can
That's
meet
exactly
in the
right.
middle.
That's exactly right.
Okay, so how uncertain are the nearby measurements? Seems to me those should be pretty secure.
Yeah, so I would say now after 10 years of scrutiny, they're pretty darn good. What I could tell you is, having made a lot of those measurements with the Hubble Space Telescope, along came the James Webb Space Telescope, and it was like, I don't know, it was like riding your first little bike when you were a kid, and then like somebody gives you a 10-speed, and you're like, oh my God, and you're like doing laps around what you did. So I've been doing laps around the work that I've been doing over the last few years, and the images are pristine. The measurements are textbook, but the answer is the same. And so the fact that James Webb is confirming what Hubble is confirming that this is a real problem.
And by
that deserves, I got to emphasize this, because what he just said is you can make measurements with whatever precision your equipment allows.
Right.
And then you extract from that an answer in the din of cosmic noise. It's kind of saying this. If you have better data and you get the same answer, You
Right.
you good.
Right.
That's right. And the signal to noise is 10 times higher for the measurement I'm making with James Webb than it was for Hubble. So if you get a full order of magnitude improvement and nothing changes, that's very compelling.
So for those at home, and in simplified terms, there was a debate. Well, maybe the math or the way we're doing the math is off, and then the Webb telescope enters the picture and tells you maybe not. So now you have to go to the idea that maybe there's something about the world of cosmology that we're not understanding, or there's something new, or
some
there's new
subtlety,
physics.
I'm going to say, or some subtlety, something being lost in translation between the universe we see and how we transform it to these sort of mathematical models. Like this is the sky, and the telescopes confirm that is the way the sky looks, but perhaps there's some subtlety in the way we translate that into math, or we translate to the beginning of time.
All right, let me go back 130 years.
Yes.
I think
That's you living in the
there.
past. Go ahead. When I was a kid,
go back then.
Yeah, let's go back.
We were riding high on classical physics.
Yes.
And people said, look, there's not much left to discover in the universe.
Right,
We
yes.
got this. We got Newton.
Right, it's all done.
We got thermodynamics.
Right.
We got this. And there are just a few clouds on the horizon.
Yeah.
That
The precession of Mercury isn't quite working out.
yeah,
right.
but we'll solve that
Yeah.
soon.
It's just another planet out there,
So
probably.
don't go into physics because
Right.
it's about to end. Bada bing. Quantum physics
Yes.
comes up, and special relativity and general relativity and all that came with that.
Right.
Is there something lurking
Right.
in the dark, in the
Right.
woods,
Right.
that will need a much bigger transformation of our understanding than just meddling
Right.
in here and there?
Right. The answer is I don't know, but what
That's
I
a
do
good answer. Good scientist. I don't know.
but I do
you know
know
what?
the
I was
process.
hoping for an answer. I got to be honest with you.
I do know the process.
I don't want to die soon.
Here's the process.
Yeah.
We're very happy with the model, the science we have. We go out and we predict experiments and we do things. And then you start to build up these cracks or tensions, little funny things. The precession of Mercury is not following Newton's theory. There's supposed to be an ether out there, and we're supposed to be traveling through it. So the speed of light should be different in different directions. We don't see that. What's going on there? You start to build up these things, and
It's like holding back the water in a dike.
right.
Right. You say you just
Right.
plug this hole.
Right.
Did that work?
Yeah,
And,
it's a
and
little
then it just
whack-a-mole.
builds.
Right.
Yeah.
And when somebody comes along, I'll say Einstein in 1916, right? He comes up with a brilliant reimagination of physics, which first does something very important. It explains or fits everything we already knew. You can't go and lose that, right? And then all these puzzles get solved. The first thing that Einstein supposedly did after he developed general relativity was he looked back at this precession of Mercury, this problem that Mercury, its orbit is itself rotating very slowly around the sun, unlike the other planets. And nobody knew why. They thought maybe there was another planet between Mercury and the sun. Einstein
Called
chose
Vulcan.
because it would be hot.
Called
there.
Vulcan. We just
very
invented.
hot.
We were perfectly happy to say it's Vulcan is there.
Yeah.
We can't see it,
But
but
it-
it's too close to the sun. It's getting the glare.
This was not unreasonable because when the planet Uranus was not traveling where it was supposed to, they invoked a planet Neptune, which they found right where it was supposed to be. So this is what makes science so much fun,
Right.
and why you can't just play the game like you're studying history and going to predict what's going to happen. Because
Right.
sometimes the planet misbehaves because there's some stuff out there you missed,
Right.
and sometimes it misbehaves because we have the wrong understanding of physics. And in that case, Einstein showed that his theory would explain Mercury's precession because Mercury was living so close to the sun, it was in what we call the strong gravity regime, where gravity was operating differently than Newton. So to answer your question, we are collecting these sort of cracks and problems, and sometimes that is the kind of harbinger of some certain sort of new revolutionary thing. Sometimes it's the loose thread on a sweater, you pull it, and sometimes it was just that annoying thread, and that's fine. Or sometimes it unravels the sweater, and it's hard to say.
Right, but we live in a society where we want answers to everything, right? And to the average person, you want an answer. But what this feels like is like you're assembling the universe using like IKEA instructions. And then you look at the manual and it's like, it doesn't look like the manual. And you're like, honey, what's this extra part? I don't know. It's dark energy. And why is there another Allen wrench? Like, and so you literally.
Well, I think what we're saying is, A, we're not done because everything isn't fitting. And B, we have this wealth of new facilities which are now coming online that really should help us answer these questions. We have the Nancy Grace Roman telescope.
So that's specifically tuned for dark energy. Is that correct?
It's going to be particularly good with dark energy.
Okay, so it's not just another telescope.
Right.
We got smart people figuring we got this problem. Right. Let's design it
but I'm
to
going to
address
ask
that problem.
what we probably you both consider a stupid question. If we don't know what it is, other than naming it dark energy, how do we know what to build to
That's
look
a great
at
question.
what is?
That's a great. So I was actually on this panel called the Decadal Survey that once every decade recommends what to build next. And this is what we thought about. And we recommended this in 2010. And the reason is because it takes us decades to build these things. So what if the science questions change as you're building or the techniques change? So we designed the telescope to measure the current techniques best that could be done, but also recognize that a telescope that didn't exist was a space-based telescope with a wide field of view. Remember I said earlier in this, you need a wide field of view to observe hundreds of thousands of galaxies. And that operates in the near infrared, which it's very difficult to observe in the near infrared from the ground because the sky is very bright.
Define near infrared.
Near infrared are wavelengths that are redder than red. So longer wavelengths than that.
But it's near. It sits closer to the visible spectrum than the far infrared.
Got it.
So near and far, it's stupid words, but we're stuck with them.
Yeah.
So the whole infrared part of the spectrum sits adjacent to the sits adjacent to red, orange, yellow, green, blue, violet. Sits adjacent to that. And those wavelengths that are near visible, we call those near, and then far. That's all. It's not deeper than that.
So we both build a telescope. We say, well, today this is what we would want, and we think it'll be great. But also tomorrow, this will be the capability that doesn't exist. So there's a discovery space capability where you say, this has got to show us new things because we've never looked in that window. We've never opened that door. So it has both elements.
Got it.
Very important here because that's why build something that only can see what you're looking for or expect. The breadth of those capabilities, that's what advances the field.
But what has to feel at times overwhelming to you is it's a constant moving target, right? So you've developed this telescope, but as you just mentioned a minute ago, around that, new discoveries are being made, new equations are being calculated, right? So it must be maddening because there's never a firm this is
but
it.
What I find very satisfying, I mean, when Neil and I were in graduate school, there were sets of questions about the universe, and those questions have either been answered or have changed to these other ones. So
exactly, they're not even interesting anymore.
Yeah, the story. I mean, we were all like, how much matter is in the universe, and is it going to recollapse? And that isn't even the right
one of our colleagues
thing to think about anymore.
Wrote a book called Just 3 Questions or something, or it was some title such as that. And it was because of that book that I now tell the world when they say, what question do you want to see answered about the universe? And my answer is, it's the question I don't yet know to ask because there's a vista that will rise up beneath me from research being done now so that I will then ask a question undreamt of today. That's the question I'm thinking of.
Well, and our field of cosmology, used to jokingly be said that we only had 2.5 facts in cosmology. So we have so much more information. It's such a great laboratory. Cosmology used to be considered closer to philosophy than physics, and now
there's hardly any data.
Right. We knew the universe was expanding. We knew there was radiation left over from the Big Bang. And we knew the sky was dark at night. That was about it.
There's several people thinking about this tension.
Yes.
You're not the lone wolf in this. So are you converging at any point?
So we have a fleet of new observatories coming online. We have the Nancy Grace Roman telescope built by NASA to launch next year, which will study dark energy. We have the Vera Rubin telescope. She was the discoverer of dark matter, one of them. And that is a massive ground-based telescope that will cover most of the sky every 3 or 4 days.
Yeah, I don't see that one working.
A million supernovae. That one is already working.
and
Yeah,
gotta
it's already-
contradict me all the
It's
time.
already online. It's discovered thousands of asteroids that
Right.
were not even counted.
Well, no one told me.
We have new CMB experiments, the Simons Observatory. We have LIGO is just still getting up and going and has great capability. We expect new results from Gaia. So there are a lot of facilities that really are well poised to give us answers.
So, but is there like a fight out there? Is there a cage match among you guys?
Right. So I would say 5 or 10 years ago, the folks from the CMB particularly were like, well, you local people are probably wrong because it used to be 50 or 100 and, you know, that seems like hard stuff, okay? And maybe some of us were like, Planck looks really good, but gee, I really would like some confirmation of that. So along came new facilities that allows people to check the work, okay? So from the cosmic microwave background, we've had these great high-resolution CMB experiments like ACT and SPT. One's Princeton mostly, one is more at Chicago. And though they have replicated the cosmic microwave background measurements, actually they've even pushed the Hubble constant lower, not 67, but 66.
Are these observatories in Antarctica?
Yeah, one's at the South Pole.
Right,
That's
that's
the
what I
South Pole
thought.
telescope, and the other one's in the Atacama in Chile.
Okay.
And so you need very little water in
It's
the
one of the
atmosphere.
driest places on Earth,
Right,
the
right.
Atacama Desert.
Has the-
As is Antarctica. It's one of the driest places on Earth.
And then nearby, we have seen the James Webb Space Telescope replicate the measurements, which was absolutely critical. We've seen other techniques developed that have cross-checked the measurements. And I just came back from something called the distance network. So not the distance ladder, but how do we combine all of these different measures simultaneously, taking account their covariance? And what we've learned
This
is
network, great name for that, because it all has to work together.
correct.
Yeah.
It's not just a ladder anymore, but it's like, but what if I have this information and this information? Well, this information was calibrated the same way as this, but it gives me a unique measure to something else.
It reminds me of this stupid comic where the Transcontinental Railroad, and there's the Golden Spike, which is
Yes.
the last spike.
Right.
And the railroads come, and the tracks don't match up.
Well, that is the problem. Hey, they're down there.
I told you we were off.
Right. So we've seen a lot of cross-checking, and this problem is not going away. It's been getting stronger and stronger. So I think we have to think hard about what it means.
Has your position altered at all, or at one point you said, I think the universe is giving us a lesson in cosmic humility. It doesn't seem to be following the manual we had.
Yeah.
We can rule out a measurement error as a cause of the Hubble tension with very high confidence.
Yes.
There's some people out there that would sort of say, perhaps not. And then
Well, are you a groupie? You're quoting him from some other program? We have him here.
You know.
We would have
Well,
quote him
he
from
doesn't know
wherever
what
he was.
he doesn't
Well, let
know
me-
half the
let
time.
me-
He doesn't know what he says.
Let me define error. Do you ever watch baseball?
Oh yeah.
You know baseball?
Yeah,
Okay.
yeah.
So
This is
Aaron,
America. What do you,
Yeah.
who do you think you are?
Aaron
There's
baseball,
a quarterback. There's a
That's
wide
the-
receiver. No. Yeah.
So I like baseball that they define an error as there was something that was supposed to be done. You know, you're supposed to field a ground ball and you messed up, right? And it didn't happen and they score that as an error, okay? But, you know, making some extraordinary play like climbing the wall and stealing a home run and not doing that is not an error, right? So in our parlance, I would say we are convinced after 10 years of scrutiny that we're not making an error in the baseball sense, that everybody
In terms of measurements and so forth.
everybody appears to be
Important
following
place
the
to be.
manual carefully. Everybody appears to be measuring what they said they're measured. The data is public. This is very important. Unlike back in the 50 or 100 days, half the battle was people had their secret photographic plates in their drawer. And so you'd have a battle and you were like,
None of the draws
yeah,
in the drawer.
sorry. That isn't where
You guys are freaks. This guy's walking around with a piece of metal in his pocket. You got stuff in your drawers.
So what's important is all the data that I talk about is in a public archive. So I say this star is this bright. It's right there.
I'm sorry, back up on the 50,
Wait,
100.
just be clear. So I can verify that, and I don't have to think that. I don't have to just take his word
No,
for
I understand, but
Correct.
back in
That's
the
important.
day, what do you mean there was secret? You were not
Well,
publicly.
If you were
revealing?
Hubble, literally the guy, right? You would go to the 100-inch telescope, you put in a photographic plate, you'd take your deep exposure, and it was your plate. You took it home to your
There was no
laboratory.
intranet.
And you told people what it said.
Yes.
But
But there were
could-
lectures about it and so forth.
No, but
and
no one
writings.
else had access to
Right.
your data.
Right.
Now everything is digital.
Right.
And
It's
it's
just
The point being, you've got a lot of people cross-checking and
correct.
checking
And so this has
double
been the
and triple checking.
democratization
Got
of
it.
science
Very
through
important.
these facilities. And so what I will say is, in the past, when errors are made, and errors absolutely happen, the baseball kind of errors, our community is so good at jumping on those, right, that I would say within weeks or months, that is found. When something lasts 10 years, when the data was public, when people could scrutinize it, then those become the things that are real things. So,
and you want to also watch out for whether there's groupthink.
Yes.
And if multiple teams who are otherwise competitors find agreement in what your measurements are, that's a good place to be.
like there were two groups in the last couple weeks that were using JWST and this method called tip of the red giant branch, and they got 74 and 75. They're unrelated to the more traditional groups that were working. And so the more you see these groups that are independent.
So the value of the Hubble
That's
constant.
correct.
Yeah,
That's right.
74,
Does the 74, 75 versus vis-a-vis 72, 72, does that trouble you?
No.
Is that,
No,
It's
it's
close
down
enough.
with the 60.
It's close enough.
Yeah,
One in
no,
the
right.
60s.
I mean, the full range of measurements people make locally is about 70 to 75. And
Got
so
it.
that's normal. That's kind of a bell curve distribution. So people, the middle is probably around 73, but some people get 75 and some get 70. But the point is,
And you
why
expect that in any random distribution.
The question is,
measurements.
why is everybody getting something higher than the early universe at 66 or 67? And I don't see how that happens by chance.
There is this theorist, Thomas Burkitt, and sort of has another explanation for all of this, and I wanted to get your thoughts on that.
So he is a theorist. He's not making measurements. And he has had a theory for a long time that when we look out in space, we use this approximation. We say everything is smooth-ish, okay? And we can use Einstein's theory of relativity as though if I have a certain amount of matter, it's kind of uniformly distributed in space. In reality, space is quite chunky.
Bumpy
and he is
whatever.
saying that the mathematics of calculating Einstein's general relativity through chunky space won't be the same as calculating it through the same amount of matter smoothly distributed. And I know a lot of people disagree with him. He's sort of on an island about this. They're devilishly difficult calculations to do analytically. So people have done it numerically with computers where you just kind of trace a particle and you have it go through all this. And people who do that say they don't get what he gets this way. But I'm open to it. Look, I mean, if things are not fitting, you have to be open to a lot of possibilities. And so,
The more things don't fit and the longer you're in that state, the kind of more, you say, oh, who's got...
What do you got?
Yeah, what do you got?
What do you got?
Yeah, what do you got?
Anybody. Yeah.
I mean, like, for example, when we discovered dark energy, there was something called the age crisis, where there were stars that appeared to be older than the age of the universe. And that was a problem. And the solution to it was actually dark energy, because when we said the age of the universe, we were assuming that the expansion had been slowing down the whole time. And so when we said how long ago was everything on top of everything, we would get a young age for the universe, 10, 12 billion years. Once you realize, oh no, the rate we have right now is a fast rate. That's not the average expansion rate of the universe. Now let's do the proper calculation. It pushed the universe to be older, 13, 14, 15 billion years.
Adam, I don't know if you're a betting man, but what would you bet would be the solution to this?
I wouldn't bet. And the reason is because
That's not fun.
I like to think of myself as part of the crew of umpires in this game, right? So we're calling the balls and strikes. We're saying, oh, this thing's traveling this fast. This is so far away. Or
You can't
whatever.
fix the game a little bit?
I mean, that would be the problem.
You can't
is
do a
if
little
I made
Pete
a
Rose
bet.
here?
If you're umpire, you
Right.
can influence
I mean, I will
the
say
game.
this is an unusual game. This is not
Finger on the scale, as the mafia likes to do.
And so my bet is that there's something interesting going on, but what it specifically is, I don't know.
Okay.
But it's like we've got two thermometers. You're taking my temperature. One says it's 98.6, and the other says I'm at a boiling point. And you're the doctor going, it could be new physics. I don't know.
I would say
I'm gonna
you're
charge
sick. I'm willing to go and say that. You're sick.
You would be a terrible doctor.
Oh, one of the more fascinating dimensions of the moving frontier of science is when you don't have an answer to questions that have been posed, or you have data, you can't make sense out of it based on our understanding of how things should be or even could be. Then you got to scratch your head and say, do I have to give up some prior expectations, some prior assumptions that went into this understanding of the universe? Because the puzzle pieces don't fit. Until Copernicus, our understanding of the world, the universe, had Earth in the center. And how else do you explain planets going forward and backwards in the night sky? Forward and then retrograde and then forward again. They have epicycles. We got that. We got that explained. And then Copernicus comes along and says, I got a new idea. Earth is not in the middle. That's pretty serious. The sun is in the middle, and Earth is just another planet. And we're all going the same direction around the sun. And you say, okay, the math is a little simpler, but the idea doesn't sit right. The epicycle thing, that kind of matched the data. And so now, what did they do? They said, well, let's check the model. So they checked the model. And it turns out the planetary orbits were not as precisely predicted as they were for the epicycles. Do we throw away the whole thing because epicycles were giving better predictions than a sun-centered universe? Do we just throw it all away? Or maybe there's adjustment on the edges of this. Maybe the idea that the sun in the middle is what's fundamental. And Copernicus presumed that orbits were perfect circles. Why wouldn't they be? It's the heavens, it's where God is, and a circle is a perfect shape. But they weren't. Discovered by Johannes Kepler 50 years later. He shows that they're ellipses. You keep the sun in the middle, put the planets on elliptical orbits, you perfectly predict and understand the motions of the planets. We're in this interesting precipice in cosmology where, the Big Bang is pretty secure, in spite of what newspaper headlines with clickbait might have been implying over the last couple of years. Big Bang in trouble. I think it's pretty secure. If I'm betting we're going to have the Big Bang throughout this. But we're going to have to understand something else about how we interpret the early universe, how we're understanding the expansion in the modern universe. Is there some missing piece that'll make it all come together? Missing piece of understanding that'll make the puzzle pieces of cosmology come together. In a resurrection of the challenge that confronted Copernicus, we kept the sun in the middle, and we found out what else needed adjustment. And at each turn of those discoveries, we had a deeper understanding of the operations of nature. And that's what makes it all so beautiful. And that is a cosmic perspective. Adam, it's been a delight to have you come through town.
Thank you.
I don't know how often you get through New York. I know there's a lot of good, fertile brain activity in the Baltimore.
My sister lives here.
Shout out to her. There's the excuse.
Shout out to her.
Shout out to your sister. Yeah. And let that be an excuse we can exploit going forward to get you back here and catch up on whatever is the latest thinking.
Can I have your prize? I want to show it to my son. I'll give it back to you, I promise.
Is he here?
He's under my seat.
Dude, thanks for
Absolutely. This is so fascinating.
Through,
I learned a lot, and it's an honor to meet you. Seriously.
Excellent.
Yeah, great.
All right, this has been StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. As always, keep looking up.
Thank you.